now. So the wave function contains all information, and it is a single valued function. Right? In your Q and T dimensions. Which must be differentiable and you should be able to square it, get your probabilities, and you must be able to integrate it. Right. Now, the latter holds true except for continuum states. So the continuum states, think about it as a state where an electron would leave your system, right? And that basically means, mathematically speaking, your wave function goes to infinity. And so that means it's not finite anymore, you cannot integrate it. But so for all bound states, right, you do, and we said that before, you do assume this finiteness in space, right? And so as you go at infinity, your wave function should be 0. And so there is some domain in which you can integrate it, and this domain is finite and your integrals will converge. So this is sort of summarized in the statement of the first postulate. The second postulate says that there is a hero, there is a linear hero for all observables. Now, typically, but not always, so if you wish, I mean, the postulate is really just this, right? And then I am providing some more explanations to it. Typically, this hero can be found via the correspondence principle. This means this means that you first note classical mechanical expression. So you should be familiar with this from your introductory quantum codes, right? Quantum lectures. So you first note the classical mechanical expression in Cartesian coordinates. And then you replace x by x hat and your momentum by dx. Okay. Your third postulate says that the only possible measurements of some observable B are eigenvalues. Its eigenvalues. Okay. So this is the only thing you can observe are these BIs, and we discussed the probabilistic interpretation, so the quantum mechanics of the interpretation according to Born of this. These eigenfunctions, of course, must not be pathological, so must be well behaved. Which is why the position operator is so tricky, right? And that's why we devoted an entire sub-chapter to that. So this postulates 1 to 3, right? They imply H to psi to E. Let's put this as there are multiple solutions to Schrödinger equations for each state, right? And the corresponding observable of the Hamiltonian will be the eigenvalue, will be the energy of that state, as we exemplified it for the particle in the box. Now, we will in the next chapter deal with the variation principle, and the variation principle is basically one method. There are also other methods, but this is one method that gets you from your Hamiltonian, which defines your system, right, and which you can derive from the correspondence principle. It tells you how to get to this wave function, right? And now think about this. Postulate 1 says the wave function is your state, right? Is your state function, right? So this is why the Hamiltonian and the energy play such an extraordinary role in quantum mechanics. Right? You could, of course, also consider other operators and other observables. That's all good, but they will not give you the wave function. They will not define your system, right? They will not. The solution to this is not necessarily the wave function, unless, of course, they commute with the Hamiltonian, as we discussed in the theories. All right, now we can go to postulate 4 now. And in here, we have a set of eigenfunctions. They form a complete set. If 0 B corresponds to an observable so there are heroes that do not have a complete set, but then these heroes don't have an observer, okay? This is a reminder, important to do the projection trick. With the, so to do the series expansion and then the projection, right? So our coefficients are Gn, psi n. All right. Postulate 5 is that your expectation value corresponds to your observable. So your QM expectation value is this. All right. So the energy of the particle in the box is not the energy of the ground state, right? It's the average, the QM average over all your states, right? With the probability given by the coefficient squared. Now, for this, the psi has to be normalized. Now, normalized means so if psi, so here again a reminder, the probability for some state now is this GI psi, which we discussed is the coefficient squared. And now if by accident it just so happens that GK equals psi, right? Then and only then is the probability of that level 1, and hence the expectation value of B would correspond to the eigenvalue BK. Right. So that means basically that all the other basis functions do not contribute. So if you can write the full wave function only exactly using one eigenfunction, then of course that expectation value collapses towards the eigenvalue of that eigenfunction. Okay, and with this, I'd like to come to the last postulate, which we're going to discuss some more, which postulates, so up to postulate 5, the previous subtopics which we discussed, right, should enable you to understand all these postulates, right? Because of what we did so far in this course, now you understand postulates 1 to 5. And now we go to postulate 6, and this goes beyond that. So it takes a little bit more to explain it. But let me write it down first. So it deals with the time dependency, and it basically says that the time-dependent Hamiltonian operating on your time-dependent wave function is minus h bar over I dt psi t. Okay, this is a postulate, right? It's also known as the time-dependent Schrödinger equation. And in general, we cannot assume our Hamiltonians to be static, right? Over time, they should change. And so this is related to the question of what is the time evolution of your system, what is the dynamics, what is the trajectory, right? And so this expression gives you, if you wish, a recipe to see how your wave function varies with time, right? So that's what you see on the right-hand side, right? That's the dependency, it's the derivative. Whenever you wonder about the derivative, you're wondering about a dependency. So how does your wave function change with time? That's what's being quantified by this derivative. All right, so there's a differential equation of first order. And so just as in classical mechanics, the future can be predicted. Now, let me qualify this some more. What is the difference is that we don't predict the future of individual particles, but rather we predict the future of our probabilities, right? So imagine the probabilities we discussed for the particle in the box. Now you add a time-dependent term to the Hamiltonian of your particle in a box, let's say an oscillating field, right? Then you can predict how these probabilities of your particle in the box will change with the time that affects the field you are applying here, right? So the difference to classical mechanics with difference that in QM we predict future of probabilities. In other words, our coefficients squared, these are our probabilities, they are time dependent, and that then implies that our psi should look like something like this in our basis set. So we have our basis set, our eigenfunctions, right? That's we also call this the Hilbert space, right? This is our coordinate system, and now you interpolate linearly these degrees of freedom, if you wish. And this interpolation is done by these coefficients, and these coefficients change with time, right? That's how you, as the mix of your eigenfunctions, right? That you throw into your CS expansion. This mix varies with time because that's what modulates the amplitudes of your eigenfunctions. So just think about this example of a field, right? You apply this field, and you would expect your symmetric wave function to get skewed a little bit by the field, right? And so these eigenfunctions have to carry different weights then, right? And that's what we express here. So we have these coefficients that are time dependent times our eigenfunctions, but the eigenfunctions, they don't change with time. They are the same. Right? So it's just the coefficients in front of them. So this is where the time dependency enters. Time dependency enters series expansion of psi in GI. Okay. So if we'd like to briefly consider now the case that actually, so if your Hamiltonian is really time dependent, just for instance with an oscillating field, that is actually it complicates, of course, the search for the solutions, right? So what is typically done is to consider as a first simple case the time-dependent Schrödinger equation for a Hamiltonian which happens to be independent of time. Right? Now you might wonder now why do we need this, right? Well, you could consider that there was some perturbation at some point, right? Let's say you excited the system, or you had a field and then you switched it off. And then you consider, then you just watch the system relax. You want to see how the wave function relaxes, but your Hamiltonian doesn't change it. Right? So this is a case we'd like to consider now. So h is not a function of time, right? Which means there's no continued external perturbation. Right? That means then we basically have our system's Hamiltonian, like we are used to. You have some wave function, and this must be your energy. And according to postulate 4, right, the postulate 6, this must be equals this, right? So you have a number times the wave function equals a derivative of a wave function. And so this is a simple differential equation which you learned to solve in high school. So the typical ansatz for this is, of course, to use an exponential function. Right. To differentiate this thing with respect to time, you immediately see you can recover this prefactor of the energy. You can pull down the exponent, right? And all other factors you throw into the prefactor A. So this ansatz is with a little bit of experience, it's quite the obvious thing. So then we have a time independent Schrödinger equation, but the entire wave function should be now something that depends on Q and T, right? So from this little consideration, we can do a product ansatz for our actual wave function, where you say, well, this could be something like e to the minus I et over h bar times a time, now this, this is our big psi and this is a small psi, times a time independent small psi q, for which we have the time independent Schrödinger equation. Okay, so this basically a product ansatz where you say my total wave function, and we sort of arrive at this product ansatz by assuming by considering this time independent Hamiltonian, right? So from this we get to here, right? And this product ansatz now nicely separates your total function into the product of two terms. One is this exponential prefactor, which contains the time, and one is the solution of the time independent Schrödinger equation, right? And so this then basically implies that this e to the minus I e t over h bar is just a shift of your function, of your wave function, shifts the small psi with time, right? With time and with the amount of energy. So this is rather a formal prefactor. So there's not a lot of physics happening in there, right? But with this in mind, right, we can now presume that we're gonna consider wave functions that are eigenfunctions in which we want to expand our true wave function, right? So now we want to consider the set of functions for a series expansion. So we want to do a series expansion of our big psi, okay? And so we would say, well, let's consider this set phi n, and they all consist of this product ansatz we just discussed. And now we have this for every solution of a small psi n of q, right? So this ansatz of establishing a set of basis functions which have this shape, right? This is what we have just discussed here above, right? And this is what this is for, right? And now we have this nice set of functions, and they should form a complete set. Okay. Right. And so once we have that, of course, we can now expand our big psi in the usual way. Right. And if we write that out, we have an an e to the minus I e n h bar psi n q. Okay. So this is not a function of t, and this is also not a function of t, but this, of course, is a function of t. Now, this function is the total time-dependent function which we expand in this complete set. You should be able to completely write this. Which it is not mandatory that this is an eigenfunction of the time-independent Hamiltonian itself, right? So not necessarily an eigenfunction of H of time-independent right? But any kind of state function can be developed in this complete set, can be expanded in this complete set of eigenfunctions, right? So it basically means that we do not, if we say that this is not an eigenfunction of the Hamiltonian, it basically means that we do not worry about the energy of the state, right? So we just assume that as you switch on the time dependency, that whatever happens with the energy, we don't care, right? For now, we just want to look, how does the state evolve as a function of time, right? All right. So let's consider now the probabilities, right? As we said, the future would be the future prediction of the probabilities. So what happens with these probabilities? Right. Okay, so the probabilities would be the coefficients in front of your eigenfunctions, right? So we now have this exponential time-dependent factor that is part of the coefficient, right? So basically, our P of some state n must be this the time-independent prefactor, and then e to the minus I e t over h bar squared. Okay. Now, what is that? That is nothing else than a n complex conjugate and complex conjugate to the exponential part is we lose the sign times a n e to the minus I h, right? And so what you see is that the exponential part if I pull this together, I have exactly the same exponent. And that is that means that exponent is 0, so this is just 1. So what you see is that actually my probability for this time-independent Hamiltonian as such does not change. But what happens now as we project out our coefficients? So we consider this, right? And we say, let's have a, let's write an, yeah, the coefficient. What is in this an? Right? So we get psi q t, and we put t0 because that's where we start, and then the Hamiltonian doesn't depend on time anymore. So it's the function at t0, and so we say now this is again simply our sum over the states j. Okay, and now we do our projection. And so we need to come from the left with the eigenfunction n and then integrate. And we pull all the other parts in the sum, we pull it in front, and what's left is our tau dependent integral, so where we integrate over tau, and this of course is our Kronecker delta, as you know already. And so this survives only if an e to the minus h bar, right? That's the only term that survives in the sum. And so we can then see, if we solve this for an, that an is nothing else than our overlap integral between n and the wave function times e to the I en t0 h bar. Okay. So this is actually a time-dependent coefficient now. So we reached 11 o'clock. I'd like to take a little break now, and then after the break we will make use of this coefficient to write down a more explicit version of the wave function, time-dependent wave function, as derived from this time-independent Hamiltonian. And after that, we'll be looking at an example for this, namely for the particle in the box. Are there any questions right now? Or is this all clear? So you can always, again, write your questions also in the chat or ask the assistant, Mr. Trestman. So let's take a break and let's maybe reconvene. Okay, it's nearly 11:05. Let's reconvene at 11:20. Okay. Okay, let's continue with the lecture. We introduced this with a bunch of assumptions, right? That the Hamiltonian be time independent, but then we solve for this phase factor and we substitute it into our series expansions, and then we do the projection trick, and now we have an expression within all these approximations. We have an expression for our coefficient, right? And so we can now enter this coefficient again in our series expansion. So if you now insert in our psi, and so before we do that, right, we have here, up here, we said this is the coefficient at time 0, right? So let me introduce here at this time 0 coefficient, right? T0, right? So if we now insert this in our psi, we want to look at the expression for this as a function of t, right? So we now change back to qt, right? And that means we have this a n e to the minus I e n t h bar psi and q. And now we insert we insert in this one, right, for our an, and now we have the T0 dependent expression. Okay. Now we can unite, of course, the two exponential functions. And so we have the, let me write this out, the psi n, psi e to the minus I e n. We factor that one out. We have here t minus t0 over h bar psi q. So for a system which was time dependent, where you stopped at T0, where T0 your Hamiltonian became time independent, this is how the wave function should be moving around, right? So this is the time dependent, the time evolution of time independent Hamiltonian. Okay. So time evolution of psi for time independent Hamiltonian. Okay. So this is sort of a simpler system than the more general system, where you have a truly time-dependent Hamiltonian. But we can, for this situation, we can actually discuss the solution quite easily. And what I'd like to do now is to exemplify all of this for the particle in the box. Okay. So if until now this was very, very abstract, and what does this mean at the end? You have the sum, but then there are these exponential functions. How would this look like for an actual system? This is what we want to discuss now. So we want to discuss the example of the particle in the box for the time independent Hamiltonian. Okay. So this is basically starting where you already are, right? So you should already know the solutions to the particle in the box and the Hamiltonian. All this is known to us. In particular, what we're going to do, so we know that your set of eigenfunctions looks like this, okay? Yeah. This is our set of eigenfunctions. Now, in this case, so this means particle in the box means our Q which has many dimensions, just becomes one dimension X, okay? So that's maybe the main difference. And other than that, we can now, given the formulas from above, we can now quite easily discuss some relevant question. In particular, let's first try to answer the following question. What is the T dependence of probability density psi of T squared? Okay. So well, so let's before we answer that, we make one more assumption. So we know this, and we assume that our psi big psi, the full wave function, is simply can be expanded only in two eigenfunctions. In particular, 1 over square root 2 of psi 1 plus 1 over square root 2 of psi 2. Okay. So given that psi, what is now the time dependency, right? So we write this psi as C1 e to the minus I E1 t over h bar psi 1. Okay. So I call this C1. Above we called it A, but it doesn't really matter. So that's our coefficient here. And then we have the second part is e to the minus ei minus I e2 t over h bar psi 2. Okay. And now we insert our formula. So we have, so this comes from the projection, right? And we now put the what we have from the eigenfunction, right? So e minus I e1 t h bar. Now we put 2 over L sinus pi L plus e to the minus I e2 t h bar 2 over L sinus, and now the second eigenfunction, so 2 pi x over L. Okay, so simply basically inserted our eigenfunction in this ansatz, and we set the C1 and the C2 to what we said above here, right? So we combine these two. Then you arrive here. And now we are going after the probability. So we want to square this. Okay. All right. So we have two brackets. The first is 1 over square root of 2. And this is the complex conjugate. So we have I E1 t over h bar psi 1. Plus 1 over square root 2 e over I e2 t h bar square root psi 2 times 1 over square root 2 minus I e1 t h bar psi 1 plus. So you see how easily this ends up with a lot of writing as soon as you get into the actual examples, which is why we always like these bracket notations, etc., to facilitate things. But of course, at the end of the day, if at some point you want to really demonstrate an example, you have to bite the bullet and do it. So if we now factor this out, then we have 1/2, and we collect the eigenfunctions, right? So we have 1/2 psi 1 squared right? And the exponential terms for the same eigenfunctions, right? They are the same and their inverse, so they become exactly 1. So we don't need to consider them. And then we have 1/2 e to the minus I e2 minus e1 t over h bar. And this is psi1 times psi2 plus 1/2 e to the I e2 minus e1 t over h bar, right? So psi1 times psi2 versus the psi2 times psi1, we write it out like this. And then we have the psi2, psi1. Then we have, again, the psi2 square bar. Now, when you look at this, right, you once have an exponential function here, e to the minus ix, right? And they're the Euler expressions for exponential functions. So this is nothing else than cosine minus x plus I sine minus x. And that is actually the same as cosine x minus I sine of x. Okay. So this is from Euler. Also simple cosine rules, right? And we have something similar. So if you consider this, right, then we also have something similar here, where e to the ix actually is cosine x plus I sine x, right? So this means e to the minus ix plus e to the ix is cosine of x. It's 2 times cosine x. Huh? Okay. And since we have in these two terms, we have 1/2 in front of it, the entire expression for our wave function now gets simplified, and you can write it as this, cosine e2 minus e1 t over h bar psi1 psi2. So we have a time independent constant here, right? And then there's a cosine that contains time as an argument. So as a function of time, this cosine is moving around this cosine goes up and down, right? And you inherit the amplitude of the overlap of psi1 and psi2. And so this goes up and down in terms of amplitude. Right? So this is the oscillating refactor of psi1 times psi2 amplitude. Okay. The second question you could answer is, so you might wonder, okay, what is, how fast does this happen, right? And so, so the first question, this A question, is how does this look like as a function of time, right? This we answered now. And now we want to see how fast does it go, right? How fast does it oscillate? So you want to show that your psi squared oscillates with period of t equals 8m L squared over 3h. Okay. So that sounds tougher than it is, right? So t is time to increase cosine argument by 2 pi, right? In other words, E2 minus E1 in the time of your period over h bar must be 2 pi. And so you can solve for t equals h bar times 2 pi divided by E2 minus E1. Now, we know the particle in the box, right? So we can use those values. E2 minus E1 is h squared over 8m L squared times 2 to the power of 2 is 4 minus 1 to the power of 2 is 1. So this is 3. And so if you substitute it, you get here 8m L squared over 3h. So the pi is in the h bar, and so it cancels out, and we got exactly what was requested here. All right. So maybe this is still a bit abstract. So then what one would like to do, right, to make things crystal clear, is some graphical illustration. So we can illustrate graphically L times this, probability density versus x over L. And then we want to do this for all periods divided by 8 and times some grid spacing and time. So we are basically gridding our time now, where j can be 0, 1, 2, and so on and so forth. Okay. So what happens here? What is L psi squared? Well, you put it into your equation here, and you basically get sine 2 over pi x, where now this x is a new x. This is defined as our old x over L. Okay, so we sort of normalize this. So we plot this like that. Or you can call it y as well. Let's call it y. Plus sin sinus to 2 pi y plus 2 times sin sinus pi x sinus 2 pi x times our time dependent term 2 pi t, and this is t, and this t is nothing else than j times t over 8. Okay. So how does this look like? I can make a plot of this. Right? You can plot this function as a function now of your y, and your y goes from 1 to 0. And so for this is 0. This would be roughly how it looks like for j equals 0. If you go to j equals 2, it should look something like this. And if you go to j equals 4, it should look like this. Okay. So what are you seeing? You're seeing here the electron probability, right? Sits first on the left, and then as time progresses, it tunnels over to the other side of your box, right? So this is remember, this is, so this is minus v. Plot this into your minus v, right? And this is infinity, and this is infinity, right? So this is your box, and this is where your electron is, and it goes back and forth, right, in your box. So that's how it looks like. Right? Now this is the dynamics for your electrons or for your particles. Right? So a very crude model of what an electron would look like in 1D, right? This is how it looks like for time-independent Hamiltonian. So we just solve the time-dependent Schrödinger equation for the particle in the box, assuming that your wave function is just the first two eigenfunctions. So this is, of course, an approximation. Now let me make this clear, maybe. So this is part of our assumption here in the beginning, right? Yeah. Right. So we assume our wave function is this, an approximation, of course. So to make this exact, you would have to go up to infinity in your series expansion. On the probabilistic argument, we said we don't need, we saw that every alternating eigenfunction doesn't contribute, and we also saw that actually you rapidly decay in the importance of how eigenfunctions still matter due to their probability. So to truncate that the series expansion at some point is certainly reasonable, but here we do it only after 2. So that's that makes our life easy, of course, to calculate this, but it just means it's very approximate, right? But you have now a rough glimpse of how things could look like in reality, right? So you can imagine that this is what the electrons do around the core of an atom, right? Roughly, they slosh around that core, right? And now your atom is, of course, a 3D object. So they slosh around in 3D space, right? It roughly looks something like this, right? Now, you can put this function, of course, into Mathematica and plot this for other values of J. You could go to include more eigenfunctions to see how that looks then. You could even go to 2 dimensions, right? How does this function look in 2 dimensions, right? You don't need to know the particle in the box solutions for 2 dimensions. You just extend this wave function into 2D, and it will be sloshing around in X and Y. And that can give you more of an idea here. There's also a homepage where more such examples are given. So this is the URL. You can also check this out to see how things look like. All right, with this, I'm done with the postulates, right? The postulates 1 to 5 were sort of formal statements of what we had discussed earlier in the semester already. The statement 6 is basically the addition of this time-dependent Schrödinger equation. We discussed how this can look like in a specific example. Unless there are any questions, I'd like to already begin, since we don't want to lose time, to begin with the next chapter, which would be about the variational method.
I'm sorry, I actually do have a question.
Yeah.
And that's why would you divide, why is it t divided by 8 exactly? Why is it 8?
So this basically normalizes, you see, we have up here, we have this factor of 8 in there.
Mm-hmm.
So this makes our normalization, our life easier here. It's the period, right? You could also choose another gridding, right? So this J basically goes from 0 up to 8, right? And so you basically divided your period in 8 parts, right? So your period, if you go to 4, your electron slosh to the other side, and if you go to 8, it will have returned again. So this is J equals 0 equals 8. You see?
Mm-hmm.
Yeah, it's just a way of gridding it. It's not really important. We could have picked, you can grid your period into any other.
I see, yeah. And the equation that you entered here, you just took the assumption and put it into the wave function, and then how does this cosine end up there in the end?
So that's from this Euler thing, right? So if you look at this, right, we have these 2 E functions. So again, I'm always thankful when you ask these questions. So check out these functions, right? Okay.
Mm-hmm.
This is 2 E functions, right? And so you consider this E function here. You can write it as a cosine minus I sinus. And then you check out this E function. You can write it as a cosine plus I sinus, right? And so the 2 sinuses, they cancel with the imaginary number, and you're left with a cosine expression with a factor of 2. And so you can collapse the two cross terms, the psi1 and the psi2 here. You can collapse them into one cross term. Each of them carries 1/2, and so together it cancels with the 2 from the 2 here.
I see.
Right. And so that's how you end up with the cosine. Yeah.
Okay, thank you.
No problem. So what you see is, right, we have this imaginary space, the complex number space, which works under the hood. But as you go to the probability densities, what emerges are always real numbers. Right? And that is because it's an observable. At the end of the day, we have the hero is a real, should have real eigenvalues, and the wave function probability is something real. So this is also a nice sort of consistency check. If you at the end calculate something which is observable, and it still happens to carry some imaginary number somewhere, then in all likelihood you had a bug somewhere, or an error in the derivation. Right? This should always, as you build the inner product and take the square, all your imaginary stuff should go away. All right, thank you again for letting me clarify this. I think chances are that many others have had the same system. As always, I will upload also the recordings to YouTube. So if I went a little bit too fast for you at this point in time, you can always check there later on. So we are now in chapter 3, and the name of this chapter is the variation in method. Right. This is also known as the principle of Ritz. And there are also other names. It's a super useful theorem which is easy to show, right? So it's not a postulate, but it's something that emerges from our postulates, and it's extremely helpful. So this variational method, or also variational theorem, right, is about, it helps us to actually calculate reasonable approximations of the true wave function, right? So the tricky thing with postulate 1 is that we do have an idea of what the system should be, but we don't know how it looks like. We cannot calculate it, right? And so we approximate it with expansions in some eigenfunctions, but that's not necessarily the best possible wave function, or the actual wave function. We just know that mathematically it must converge towards this. But that, of course, also means that we sort of lose some intuition, and we view everything in this basis series expansion. And the advantage of doing this is that we can make use of this variational method. Now, what is this method, right? So this chapter has a couple of sub chapters I'd like to tell you about now. So there is first the theorem itself, the principle, the variational principle. The second is that we will see that we can arrive at a secular equation with this. And as a third subchapter, I'd like to rewrite these solutions in terms of this content in terms of a matrix. And then as a fourth subchapter, I'd also like to discuss some alternatives to the variational method. So this is our table of content for this third chapter. Right? Yeah, so we don't have much time here, but basically the point is we do not psi, right? We do know that psi is must in general offer us eigenvalue equations with the Hamiltonian, in particular in the case of the time-independent Schrödinger equation, right? Okay, so that's something we know. We know it's important, right? And we can, of course, approximate psi with some trial functions, right? So we will discuss how to do this within this chapter. And basically, we will use some expansion in eigenfunctions, okay? And the variational method will basically help us to get the coefficients. How can we? So these are eigenfunctions of H, right? You've seen some, for instance, particle in the box, hydrogen atom, whatever. So you know this, but the variational method will tell you how can we obtain the coefficients. Once you have the coefficients, once you have the eigenfunctions, you're good to go. You could calculate any observable, right? And you have understood. You represent your system according to postulate 1 by that sum, by that expansion. All right, that's what I wanted to tell you as an introduction to chapter 3. Tomorrow we will hopefully get to subsection 1 and attack subsection 2. Are there any questions? It's not the case. I'd like to thank you for your attention, and I'll see you tomorrow. Bye-bye.